Have you ever noticed how your hot cup of tea gradually loses warmth as it sits on the table? The heat doesn't just disappear, it flows into the cooler surroundings. Now, imagine if we could capture and measure every bit of that escaping heat during a chemical reaction. Well, scientists can, using a clever technique called calorimetry. Today, we'll uncover how chemists measure the energy released or absorbed in reactions like burning graphite in pure oxygen and how they translate that into precise values of internal energy called delta U and enthalpy called delta H. So, what exactly is calorimetry? In simple terms, calorimetry is the science of measuring heat changes. To do this, we place the reacting substances inside a special insulated container called a calorimeter. This device stops heat from leaking out into the surroundings, allowing us to keep track of exactly how much heat flows. Depending on how the calorimeter is set up, it can measure times heat at constant volume, which we call Q sub V, times or heat at constant pressure, known as Q sub P. For example, when a fuel burns in a bomb calorimeter, the volume stays constant, making it ideal for calculating internal energy. On the other hand, reactions in an open beaker happen at constant pressure, helping us find enthalpy changes. Ready to see how it all works? Let's dive deeper. To measure the change in internal energy, delta U, we use a bomb calorimeter, a strong steel vessel that can withstand high pressure. Here's how it works. Times we place the sample, say 1 gram of graphite, inside the bomb and fill it with pure oxygen. Times then, we seal the bomb and immerse it in water. Times when we ignite the sample, it burns completely. Times the heat released warms the water around the bomb. To calculate the heat, we use this formula, Q equals C multiplied by delta T, where times Q is the heat absorbed, times C is the heat capacity of the calorimeter, times and delta T is the rise in temperature. Because the volume doesn't change, no work is done, and that means delta U equals Q sub V. Think of it as a snapshot of all the energy released during combustion. Next, let's talk about measuring enthalpy change or delta H. Most reactions in the laboratory happen at constant pressure, like atmospheric pressure. Here, we often use an open calorimeter, like a simple insulated cup or beaker. In this setup, delta H equals Q sub P, which means the heat measured at constant pressure directly gives us the enthalpy change. For example, if you melt ice in an open container, the heat absorbed equals the enthalpy of fusion of water. Simple, right? But incredibly powerful when you want to track energy changes accurately. Let's make this real with an example from your textbook. Problem: when 1 gram of graphite burns in a bomb calorimeter, the temperature rises from 298 Kelvin to 299 Kelvin. The calorimeter's heat capacity is 20.7 kilojoules per Kelvin. Step 1. Calculate the heat absorbed. Q equals C times delta T. So, Q is equal to 20.7 multiplied by 1 is equal to 20.7 kilojoules. Since heat is released by combustion, delta U equals minus Q or minus 20.7 kilojoules for 1 gram. Step 2. Convert to per mole. 1 mole of carbon weighs 12 grams. Therefore, delta U is equal to minus 20.7 multiplied by 12 is equal to minus 248 kilojoules per mole. Because the reaction happened at constant volume, delta H equals delta U's answer. Combusting 1 mole of graphite releases 248 kilojoules of energy. This precise measurement helps industries control fuel efficiency and calculate energy balances. Let's tackle one more example. Problem: calculate the internal energy change when 1 mole of water vaporizes at 373 Kelvin. Given delta H equals 40.79 kilojoules per mole. Delta N gas equals 1. R equals 8.314 joules per mole Kelvin, which we convert to 0.008314 kilojoules per mole Kelvin. Step 1. Calculate the correction term. Delta N gas times R times T equals 1 multiplied by 0.008314 multiplied by 373 equals 3.1 kilojoules. Step 2. Find delta U. Delta U equals delta H minus this term. 40.79 minus 3.1 equals 37.69 kilojoules per mole. Answer. When water vaporizes, it absorbs 37.69 kilojoules per mole as internal energy. Alright, let's take a step back and ask, why is calorimetry so important? Think about it. Every time you eat a packet of chips, the energy value on the label, those calories, comes from calorimetric measurements. The same science helps industries measure how much energy a fuel releases so they can design engines that are efficient and safe. Here's a question for you. If you were an engineer working on rocket fuel, would you rely on theory alone? Or would you want actual calorimetry data to confirm how much energy your fuel provides? Exactly. You'd need precise measurements, and that's what calorimetry gives us. It doesn't stop there. From food science to combustion in power plants, calorimetry transforms something as simple as a temperature rise into a number that tells us how much energy is really involved. So, next time you see energy content on your food packet or hear about a new clean fuel, remember, behind those numbers lies the simple yet powerful tool of calorimetry. Now, let me ask you, can you spot one place in your daily life where calorimetry data affects you directly? Think about what you eat, the fuel in vehicles, or even the electricity that powers your home.